lot of pace nowadays, and people have started talking about reinforcement learning a lot nowadays. So those people who want to do some research in the machine learning arena and into supervised and they are supervised and unsupervised have been touched upon various researchers. So you would hardly find any domain in which you can work upon. But for reinforcement learning, it is still a new area. I won't say new, it's another 5 years back, but still it is a new area and the people have not dealt a lot on reinforcement learning. So this session would be quite useful for all the future researchers and the research scholars and those PhDs who want like to change their area. So welcome, Dr. Tausif Diwan. You can start your session now.
Thank you, ma'am. Hello, good afternoon all. So today we will try to implement this convolutional neural network for the two very famous dataset. One is Mnist and another one is CIFAR dataset. Before jumping to that Mnist implementation using this convolutional neural network, just take a look what is this dataset is all about and how the dataset is categorized into training and testing part and how many instances are there in each of these. So basically it's a handwritten digit database. So just have a look here. Total 70,000 images are there. So 60,000 images are considered as a training set and 10,000 images are there in test set. Okay. So this data is divided into 4 files. This first one is nothing but the training set images. Just see, this is the images and corresponding label is stored here, the training set labels. So 60,000 images are stored here and the 60,000 labels are stored in the second file. Then test set images are there, which is stored in third file. The 10,000 images are there and this is okay. So the size of one image in both of distribution is coming from same distribution. Okay, so this was all about the Mnist dataset. Now see how can we use this or how can we do the implement the CNN for the Mnist dataset. If any point of time, if you are having any doubt in this implementation, then you can ask. So first of all, we need to import. Okay, we are implementing it using Keras. Then we will see one more example in which we will be importing using TensorFlow. Keras is just a high-level framework on TensorFlow. Basically, when we want to do something from scratch, then we should go with PyTorch. Otherwise, we can go with TensorFlow. And if we are working with high-level APIs only, then we can go with Keras. So here we are importing these libraries. NumPy is imported. Then TensorFlow is imported from Keras is imported from TensorFlow, and the layers are imported. Okay, the imported layer can be directly used. So which are the various layers that can be used? Convolutional layer, dense layer, pooling layers, and importing the execution of this.
Copy, sir. Copy. Take your food, sir. It's very sincere in doing counts.
And here the data set is categorized into 10 categories. So it may be handwritten digit 0, handwritten digit 1, handwritten digit 2, up to handwritten digit 9. Okay. So here we are describing this number of classes is equal to 10. Then the input shape we need to do in terms of 28 cross 28. It's a grayscale image. That's why the depth is equal to 1. After that, we need to assign it to these variables to set training images, testing images, training set labels, and testing set labels. So 4 variables are there. Just import this keras.dataset.mnist. This dataset is already available in keras.dataset. So we assign this 4 files into these variables: training, testing, and the labels. After that, if you look at the one image, like 28 cross 28 values are there, the value lies between 0 to 255. Okay, then at the end, what we will do, we will apply some sort of normalization to better converge our model. Then what we will do, we will just divide each and every value in that 28 cross 28 matrix by 255. And how can we do that? Xtrain dot S type divided by 255. So each and every value is divided by 255, and the largest value is 255 in that matrix. So when you perform this step, then each and every value comes in the range from 0 to 1 only. So it is called a normalization. After doing this normalization, previously the values was stored in the form of a matrix. Okay, now this matrix is get converted into a vector with the help of this np dot expand dimension. Okay, so here it is considered as a transformation of matrix into vector. Similarly, xtrain is also converted and xtest is also converted. After that, what we are doing, we are printing this, the shape of training data, shape of testing data. Moreover, we are also printing that how many training set images are there and how many testing set images are there. Lastly, in this, we just convert this into categorical form. Like suppose if one image is there, this image belongs to and return digit 2. Okay, then what we want it to be converted into a vector. Total how many categories are there? 10 categories are there. So we want that output should be converted into a vector of size 10, in which all the values will be 0 and except that second position value will be 1. So for that we use this utility function keras.utility.toCategorical. So training set label as well as testing set label, these are converted into for the better representation of legal form, for the better representation. Now see, this is the output. First of all, it is getting downloaded. Then we are printing 4 things. Okay, just look at this. These 4 things we are printing. First, shape of the training set. So 60,000, 28, 28, 1. This is the shape of that tensor. Okay. Then testing set 10,000, 28, 28, 1. This is the shape of testing set. After that, xtrain dot shape, we are accessing the very first entry in this. So this is 60,000. 60,000 training samples is get printed out, and here 10,000 test sample is get printed out. Fine. After looking at this data, we form our model. This is the most important thing that we were discussing yesterday also. We build a sequential model. Sequential model means one layer is there, after one another layer only. Okay, so the layers form a sequence. It is not possible that you can directly convert first and third layer in sequential model. Okay, so keras.sequential, using this we can generate the model. So the very first layer is considered as input. So keras.input is equal to shape, and here we are passing input shape. What is input shape? Have we defined this? Yes, we had already defined the input shape. Just look at this. Input shape is this 28, 28, 1. This is our input shape that we are assigning over here. After this, we are applying convolutional layer. So it is a 2D convolutional. We directly use this conv 2D. Now see the matrix of this. Here 32 indicates that that the total number of filters that we are applying. Filter size is 3 cross 3. Which activation we are using? ReLU activation that we are using over here. Do you want to see the syntax of this? What we can do? Just see the layers dot convo 2D in Keras. So you will get the syntax of this. You will get what is this first parameter. Just look at this tf dot Keras is this layer that we are using. The first argument represent how many filters we are using. Kernel size is what, stride is what, padding is what. Okay, so all these are the parameters that can be used over here. We may not some filters are assigned. 30 filters are used in this convolutional layer. Filter size is 3 cross 3 and activation function is ReLU. Are applying this. This will be considered as a second layer. Input layer is the very first layer. In the second layer, after that we are applying max pool 2D. Okay, so this is max pool 2D, pool 2D. This is max pool 2D. The same convolutional layer that we have. The second filter size reference is that in the previous convolutional layer we were using 32 filters. Here we are using 64 filters. Then one max pool. After that, flatten layer means that volume should get converted into a vector. Okay. Then we are using dropout. Don't worry about dropout at this point of time. It is basically used for providing the regularization so that our model should perform well on the data that it has not seen before. Then last layer is the dense layer. How many neurons we are assigning in the dense layer? Once again, number of classes. How many classes are here? 10 classes. This we have already defined earlier, and the activation here is the softmax. So it computes the probability. So this is the model architecture. After defining this model, we want that whether we constructed that model successfully or not, and what is the characteristics of that model. So we can print this model using model.summary. Using model.summary, you can print. Just see, I'm running this cell. Now see, this is the output. Fine. Layer, output shape, and number of parameters. This is the very first layer, convo 2D. Okay. The input it is applied first convolution 28 cross 28 cross 1. On 28 cross 28, we are applying 3 cross 9, 3 cross 3. Okay. Then how the output size is computed? 28 minus 3 plus 1 comes out to be 26, 26. Fine. And how many filters we are applying? 32. That's why 26, 26, 32. How many parameters are involved here? 3 cross 3 filter is applied on a volume which is having depth 3. So 3 multiplied by 3 multiplied by 3. This is 27 plus 1. 28 parameters are there for one filter. How many filters we are applying? 32. So 28 multiplied by 32 is nothing but this number of parameters. No, we are applying these 3 cross 3 filter on a grayscale image. Okay. What is grayscale image? 1. So 3 cross 3 filter is applied. So 3 multiplied by 3 multiplied by 1 only. Okay. So 3 multiplied by 3 multiplied by 1, it is 9 plus 1 bias. So that is 10. 10 multiplied by 32 is nothing but 320. 320 parameters are associated with this. Okay. See here, you can also print the parameter. After that, we apply this max pool 2D. So 26, 26 is getting transformed into 13 cross 13. Okay. Depth is not getting changed over here. 32 will remain as it 32 only. No parameters are associated as it is a pooling layer. Then next convolutional layer. See here. Name here is convo 2D and here convo 2D underscore 1. We have defined this. Okay. Default. It is defined like this is we have like first convo 2D, second convo 2D, but what is the name of that convolutional layer? It is decided by the framework. Now 13 cross 13 is getting transformed to 11 cross 11. And how many filters we are applying? 64 filters we are applying. See, this 3 cross 3 filter is applied on a volume which is having depth 32. How the parameters are getting calculated? 3 multiplied by 3 multiplied by 32. These many weights are there plus 1 bias. Okay. So these are the number of parameters associated with single filter. How many filters we are applying? 64, the entire effect is 64 comes out 496. After that, max cross 11 we apply 2 cross 2 max pool, so it is getting converted to 5 cross 5 is getting converted to 5 not valid, and this is not valid, it is generated over here. That is not getting changed. Not there means can't change. So the volume 64, it is getting converted to a vector. This volume 4 to a vector. So 564 it is nothing 1600. After that dropout, once again 1600. Then dense layer is there, so 10 neurons are assigned for here in the dense layer. So we can compute the number of parameters. 10 multiplied by 1600 plus 10 bias will be there, so 16,010. See here, if you sum all these parameters, it is nothing but 34,826. These are the total parameters, and among these parameters, the parameters are divided into two categories: trainable as well as non-trainable parameter. Here, as such, no non-trainable parameters are there. Then you can see here, this is trainable, and total number of trainable parameter and total parameters are same. If you can use some sort of transfer learning in which, if we take one example like 20,000 is the total number of parameter and 10,000 are the trainable parameter, and the remaining 10,000 that we will be using from the pre-trained CNN. In that case, so trainable parameter would be 10,000 and non-trainable parameter would be 10,000. After that, okay, first I run this cell and then I'll explain what is happening over here because it will take. So here batch size of 128 assigned. What do we mean by this? Total training size is 60,000 images are there. When we say batch is equal to 128, then what is happening over here? 128 random sample from the 60,000 is taken. Okay, and after that backpropagation is running over here. Gradient descent algorithm is running. In model.compile, we need to define these three things. Which loss we will be using? So critical cross entropy loss that we will be using. Which optimizer that we are going to apply? So Adams optimizer, which is a combination of momentum and RMS prop, and on which matrix our model will be evaluated. So accuracy is the most preferable model, and here also we are using accuracy. Model.compile, after that we use this model.fit. Model.fit is nothing but the actual model training. Okay, for training the model, which parameter that we will be passing? Training set images. So this is this X train, then label, corresponding label, Y train. Okay, batch size is equal to batch size 28 equal to epochs. Epoch is nothing but consideration of all the samples in the training set. Okay, total 60,000. So one set of 60,000 is nothing but one epoch, and second consideration of 60,000 is nothing but second epoch, like this. For 15 epoch we will be running our model, and validation split is for 10%. What do we mean by this? Among the 60,000 sample, 10% samples are kept as a validation set that we will be using at the end of each and every epoch. Now see how the output is getting printed over here. Just try to understand this. Here, this is the very first epoch. Okay, here the loss is getting printed. This loss is nothing but training loss. Okay, this accuracy is printed. This accuracy is on the training set. At the end of this epoch, we will compute the loss and accuracy on the validation set. Well, validation set is nothing but that withheld data. Okay, so we will just compute loss on the validation set and validation accuracy. After that, the second epoch will get started. You just look at this. Here, the loss is getting reduced, the training accuracy getting increased. Moreover, you can see that validation loss is also getting reduced and validation accuracy is also getting increased. It will take time. This first epoch, we are running it for 15 epoch. At the end, we will evaluate the model. What do we mean by evaluation? Evaluation means how the model is performing on the test set. Test data means this data which the model has not seen before. Okay, so we just print the loss, the training testing set, and accuracy on the testing set. This was all about the implementation of convolutional neural network on MNIST dataset. Any question, any doubt? Should we see one more example here or we all reinforcement learning? See here, this is one more data set. It is also very famous data set. It is a CFAR 10 data set. Here 60,000 images are there, but it is a colored image. Okay, the size of one image is 32 cross 32 cross 3, which is categorized into 10 categories. Okay, so here these categories are there: airplane, automobile, bird, cat. Okay, suppose if I want to build the classifier, CNN classifier for this using TensorFlow, then I can write like this. First import these libraries. Okay, then after that load this dataset.cfar10.load data, normalize the same thing that we are doing. After that, just define the class name. So 10 categories are there. What we can do after this, we can just plot this some of the images. So here 0, it is a range of 25, means it is running from 0 to 24. So total 25 images are getting printed out over here. Moreover, the label of those images are also getting printed. Just see, this is a frog image, this is a truck image, like this. So total 25 images are getting printed out over here. After that, we construct the model, which is once again sequential model. In sequential model, we add these layers. First, convolutional 2D. Here we are using 5 cross 5 filter, and 32 filters are applied over here. Then one max pool 2D, then one more convolutional layer in which we are using 3 cross 3 filter. After that, we are using some dense layer, this. Okay, so first convolution, second convolution, third convolution, and fourth convolution. Okay, and we can just print the model.summary. Here you will get this, which layer we are using, what is the output shape, and how many parameters that we are using. After that, we add some more dense layer. So first of all, before applying dense layer, we apply this flatten layer. Then first dense layer with 64 neurons, second dense layer with 32 neurons, and last dense layer with 10 neuron, because it is just 10 categories are there. After that, once again we are plotting this summary, model.summary. Here we can see the entire summaries get printed out. First 4 convolution followed by flatten, and then 3 dense layer. This is the total model summary. In model.compile, we need to define the same 3 things: which optimizer that we'll be using, which loss we'll be using, and which matrix that will be used for the evaluation of the model. After that, the actual model training will start on the training set. Along with this training set, we are also providing the label. It is a supervised category. For 5 epochs, we run this, and validation data is equal to test images and test label that we are also providing here. Okay. Here also we are plotting the plot between the accuracy versus epoch, like how the accuracy is getting increased after subsequent epochs, and this is accuracy and this is validation accuracy. You just have a look on both of these, and at last we just print the test accuracy. Okay, so this was all about the CNN implementation. Okay, so next we start with this reinforcement learning. Okay, in this will be the content. First of all, we will see the types of learning in brief, then the various application domains in which reinforcement learning is used. Then we will see the backbone of this reinforcement learning, that is nothing but the Markov decision process. And we will see one example in the context of Markov decision process. And along with that, we will see some important concept and terminologies for this reinforcement learning. Yeah, we had already discussed this, and just have a look. Supervised learning, in which we are providing labeled input. In unsupervised learning, we are providing unlabeled input. Examples under this category, classification and regulation for clustering in case of unsupervised learning, PCA, principal component analysis, LDA, linear discriminant analysis, ICA, independent component analysis. All these comes under the unsupervised category. Semi-supervised category is just an extension or mixture of both of these, in which some of the examples are labeled and some of the examples are unlabeled. The last one is the reinforcement learning that we are going to discuss today, in which we will be interacting with the environment. Okay, and later on we can receive some sort of reward function. It may be positive reward or negative reward, that is once again passed to the agent, and once again agent will perform the action depending on the reward. Okay, so this is just an interactive kind of learning. This is the illustrative form of all these kind of learning, in which one question is there, is PCA is also unsupervised? Yes, PCA also comes under in unsupervised category. So here we just provided as input features plus label. Okay, and this output is the prediction. In unsupervised, we give input as features and we find this pattern in the data. However, in reinforcement learning, some sort of actions and a set of states are given as input, which is further accumulated in the form of a reward, and we will find the best action suited for the process. And what is the difference between reinforcement learning and other kind of learning? Here, see, there is no such supervisor as it was present in case of supervised learning. Here, we do not train with a large unlabeled or unlabeled pre-collected data set, as we are doing in case of supervised learning, or in case of unsupervised learning. We had seen the example of this Mnist, in which 60,000 labeled examples are there. And on this 60,000 labeled example, we are running our classifier. Moreover, there is a very much problematic situation when we are not having any labeled classes or labeled, because various types of annotation and the problems in annotation is also very huge. Okay, so this reinforcement learning is getting very popular, and here the data is provided to you is dynamically via feedback. Okay, means the feedback is generated at runtime, and that feedback is given as input for the next step or for the next time step. Here, iteratively, you make a decision, because it's not a single decision, it's a chain of decision that you take over a sequence of time step. Means what is the sequence, or what is the result, or what is the decision taken at first time step, what is the decision taken at second time step, and so on. And these sequence of decision form a final decision. Suppose we take an example of classification problem, in which you just run an inference on the data and just produce the output. But it is not the case with reinforcement learning. In reinforcement learning, you first run your inferences repeatedly, then navigating through the real world environment as you go. Then the various kind of problems that can be solvable using reinforcement learning. So we will take the detailed section in the next slide. In robotics, text mining, trade execution, healthcare, gaming, these are all the what we can say. These are the various fields in which reinforcement learning is performing tremendously well. Suppose if we take an example of robotics, so one robot is there, then we want to train a robot for picking an item from the table and putting it on the another table. Okay, so this is just an example for which we can train the robot using reinforcement learning. So it is also high dimensional control problems and various types of input that can be given at various time steps. Based on that, he will perform the operation. The robot will perform the operation. Another example we can consider as text mining. The text generation models are there, like what will be the generation of which word will be generated in the next time step, and depending on that, the next word will be generated. So this type of problems comes under the category of the sequence modeling, and here also reinforcement learning is performing very well. The trade execution, like what is the scenario at time step T, what is well suited for reinforcement learning, and based on that we can take the decision, financial decision, that we should sell any particular trade scenario at in healthcare also. Like how can we correlate this healthcare, or how the robotics or reinforcement learning is used here? Various types of medications are there. The various stages of medications are there. Like you can give the first medication and you just see like how our body is reacting to that medication, and depending on that we just apply the second dose, or we just change the medicine, or like that. So depending on the behavior of the body of the patient, we decide the first second decision. That is nothing but an example of reinforcement learning in healthcare. Gaming is a very what we can say the mostly used reinforcement learning is the field in gaming. So game is nothing. Suppose if we take a Sudoku puzzle, or if we take any tic-tac-toe kind of example, or if we take an example of chess playing, where you just move to the first step, then your opponent will take second step based on your second step. These type of problems, all these problems comes under the reinforcement learning category. We just need to ensure that some sort of sequences are there, and each output is considered as a decision, and these outputs comes under the different time steps. Then you can go with the reinforcement learning. So the overall intuition is like that. Suppose one baby is there, and two things are there. Suppose he can touch the fire, or he can touch the milk. Okay, if he touches to the milk bottle, then nothing will happen. Okay, so it can be considered as a positive reward. And if he touches to the fire, then some burning will be there, burning sensations are there. Then in the near future he should not touches to the fire. So this is the overall intuition behind the reinforcement learning. Now coming back to the backbone of this reinforcement learning, known as Markov decision process. Before getting into the depth of Markov decision process, first we will see where it is coming from and what is the meaning of weak law of large numbers. So what this weak law of large numbers says that when you collect the independent samples, and when at some point of time the number of samples get very high, okay, then it says that the mean of those samples converge to the mean of the true population. What is the difference between population and sample? See here, a very huge population is there. Population means the consideration of all the samples. Consider that 1 million samples are there. Okay, this is considered as a population. We are not interested in performing any kind of statistics on the entire population. Then what will you do? You perform sampling. You take 1000 sample from that, and you perform operation on that sample, and you get the output. Now the problem is that whether the sample is truly representing that population or not. Means some of the statistics are there which is not get captured by that sample. This is the main problem in various kinds of sampling. So what it says that when the samples are independent, then if you get sample or if you take multiple sample, then the mean of that sample is nothing but the mean of the population. Is that this independence was not a necessary criteria. It may be that possibility that the samples are dependent on the other. So here, if you take any sequence modeling in which first decision is dependent on previous decision, third decision is based on the previous two decision, like that. So that is nothing but a consideration of dependency among the samples. Markov believed that independence was not a necessary condition. It is also possible that the samples may be dependent. Then also the mean is getting converged to the mean of the true population. This is explained with the help of an example in the subsequent slides. So here process involving dependent random variable is also getting converged over a time. Okay. Now, if you want to formulate your problem with the help of reinforcement learning, then first of all, you should structure your problem as a Markov decision process. If you can structure your problem as a Markov decision process, then only you will be able to, you will be in the position to apply reinforcement learning on that particular problem, otherwise not. So this is the first and foremost step to structure your problem as a Markov decision process. How can you structure your problem as a Markov decision process? Before that, just look at this chain. It is also known as a random chain of some sort of dependencies are there. Okay. Now see, it's a way. Markov chain means it's a way to describe how randomness or stochasticness are there in the system and processes, and how these dependent or some sort of independent, what we can say, some sort of stochastic properties are there, and in this stochastic nature of systems or processes are getting evolved over time. System is modeled as a sequence of states. What is at state 0, what is at state 1, what is at state 2, like that. So it is nothing but a sequence of states. Okay? And here each and every states are connected. When each and every states are connected and it is a sequence of steps, it form a chain, and this chain is known as Markov chain. Transition between the state are conditioned. What do we mean by this? Suppose you are at a particular state, what will be the next state? It is just a conditional probability. Okay, some sort of dependency is there. What state will be the next state? Okay, it is not purely independent. So this type of dependency is there in this Markov chain, and it is the transition or the transition that is taking place from state I to state I plus 1. It is not completely independent process. What this says is, as long as you can reach to all the states in the chain, probability of that particular state that is converged to single state in the long run. Here it is saying that, suppose consider that 10 states again, and you can start from any state, you can reach to any other state. Okay, so in a long run, it does not it does not matter that whether the states are dependent or whether the state is independent. It says that in a long run, it is getting converged irrespective of the dependency among the states. In Markov chain, all the states are observable. So what do we mean by this? Some sort of in some of the problems, some states are there which are non-observable. You might have heard about that hidden Markov model, in which some of these states are observable, some of these states are non-observable. So those kind of models comes under the category of hidden Markov model. As of now, we are not considering that in our today's lecture. So we will be talking about only observable states. One researcher, Shannon, it uses the Markov chain for the generation of English words. Like English word comprises of several English alphabets. Okay, then what it says that the word that is generated or the character that is considered at any point of time, all the characters that is already generated in the previous time states. Okay, so dependency is there, but these ways happen to some of English language. What is the advantages of this? See, if you take any real life example, suppose if we take an example of parking lot example. So various types of characteristics are there in a parking lot, like the day of the week, then we can say that the which time that you are using for parking, what is the fee of that parking, proximity to transit, then proximity of busyness, a number of free parking slot in that vicinity, number of available parking slot. So all these are the characteristics. Based on that, you will take the decision whether we should park or not. If you park, then in which slot you will be parking. So these kind of problems are there. Okay, and more realistic type of questions can be asked. Like which type of question? See this. In what state is the system doing to be in n time steps? Means if we consider an example, what is the occupancy rate of the parking lot after 3 hours at this point of time? Okay, so this type of questions can be asked, and for answering this type of question, we need to solve this problem using reinforcement learning. For structuring that problem, first of all, you need to structure this using Markov chain process. Another type of question, it may be asked, like when the system goes from state A to state B in n steps. So this type of questions, if we take an example in the context of parking lot, so it could be, what is the likelihood that it follows a specific path P? Suppose if we take this, how likely is the parking lot to be at 50% capacity and then 25% capacity in the 5 hour? What is the chances of this? Fine. See one more example. This is a very realistic example that we will going to consider, and we will form the Markov chain for the same. Several set of states are there. Suppose if we take a workout routine example, which these are the 4 workout set: running for 3 miles, 20 push-up, 15 minutes rowing example, and then 20 pull-ups. So these are the set of exercise that anyone can follow. See here, is there any dependency among these? Like, is there any dependency that push-up can be done only after running? It is not like that. Fine. Even though there is no such dependency, then also you may observe some sort of pattern among these. Fine. Preferably, it is also possible that you may adopt this pull-up after this push-up only, as though there is no such dependency on this pull-up, fine. So workout routine can be modeled as a Markov chain. First of all, we see how it can be modeled as Markov chain. In Markov chain, we use this short-term memory. It just remember the current state, where you are currently, and what is the things that needs to be stored for the current state. Which type of question can be asked? See, if I start the workout with a run, how likely am I to do push-up on the second set? What is the possibility or what is the probability that I will do push-up on the second set? One more question like this. In a 3-set workout, what do we mean by this? Among these 4 set, I am only preferring 3 set. Or I will perform 3 set only. I will just ignore 1 set. In a 3-set workout, how likely I am to do first run, then push up, then pull up? What is the chances or what is the probability of this? What is the likelihood of doing any of the exercise on the 4th set? So these are the very realistic question. We will also see how we can model this problem using Markov chain. First, see, this is the statistics. This is the statistics of a 62 days. Now see, this is our set running 3 miles. Okay. Now this is our next set. It is the current set. What? So running after running, it is a very rare possibility. So only one time. It's only one. 20 push-up after running. So it is taken 4 times. See here, taking push-up after running is having huge probability. Okay. Then rowing for 15 minutes after running 3 miles is taken 3 times. Then 20 pull-ups after running is 2 times. Fine. Other characteristics, when you are currently doing push-up, what is the probability, or what, how many times you are once again taking the push-up is 2 times. Running after push-up is 7 times. Rowing after push-up is 5. Pull after push-up is 6 times. This is the summation of this. 7 plus 2, 9 plus 5, 14 plus 6 is 20. Similarly, these are the another statistics. Running as a next set after rowing 8 times. Push-up after rowing 6 times. Rowing after rowing 1 times. Okay. Then pull-up after rowing is 5 times. Similarly, this running after pull-up, push-up after pull-up, then rowing after pull-up, and then pull-up after pull-up. So these are the statistics. Based on these statistics, you need to formulate the Markov chain. Now see here, if you sum all these, this is running after running, this is running after push-up, then running after rowing, and running after pull-up. So this is nothing but the running as a next set. This column will give me the push-up as a next set. This column will give me rowing as a next set, and so on. Now, first of all, convert this into the probability. So how can we convert this into probability? One time out of this 10 times, I am taking this. 4 times out of this 10 times, I am taking this. 3 times out of this 10, I am taking this. Okay, converted into probability. 1 out of 10 is 10%. 4 out of 10 is 40%. 3 out of 10 is 30%. 2 out of 10 is 20%. Similarly, here also 7 out of 20, 35%, 0.35. 2 out of 20, 10%. 5 out of 20 is 0.25, and like that. Make sure that summation of each and every row is 1. Okay, so these are all the probabilities. Any doubt till this point of time? Okay. Now in the next set, you form a transition diagram. Total how many states are there over here? Look at this. These are the set: running, push-up, rowing, and pull-up. Okay, so we can write like this: running, push-up, pull-up, and rowing. What is the probability? See here. Running after running, probability is 10%, 0.1. So we can write like this: 0.1. Then push-up after running means running to push-up, 0.4. Running to push-up. See this 0.4. Okay. Likewise, you will draw this, and this is the probability matrix P. Here I am not doing anything. I have just written all these value in the form of a matrix. Fine. After doing this, all those questions, which type of questions? This. If I start the workout with a run, how likely am I to do push-up on the second set? These type of question can be asked from this matrix. See here how we will take the first. If I start the workout with a run, how likely am I to do push-up on the second set? Now see here, we know the starting state. What is the starting state? Running. Ending state is push-up. Okay, and time frame is 2. Why? Because it is asking for the second set. Now see, what are the possibility or how many options are there? Means I am starting from the running and then I need to end on push up. Okay. On the second set. From before this second set, one more set will be there. So what I can do? Running, then once again running, followed by push up. Okay, so this is this running after running and then push up after running. Okay. After, what is the second alternative? Second alternative is this. I can do push up after running and from push up once again push up. Fine. So this, see this P of push up comma run, it indicates that probability of push up after running. Fine. Then once again push up after push up. One more possibility is there, rowing after running, okay, and then push up after rowing. So what is the sequence? Sequence is this: running to rowing, rowing to push up. Okay, here what it is asking? It is asking for start with running, end with push up. Okay. Meanwhile, you can take any other option. It may be running, it may be rowing, or it may be push up, or it may be pull up. Okay. One more possibility: after running and once again perform the push up after pull up. See, there are four alternatives. Okay, now four alternatives we modeled in terms of probability. So this is the probability of running after running. What is the probability? 0.1. Then probability of push up after run. What is this? Probability of push up after run 0.4. So what is happening over here? 0.1 is getting multiplied by 0.4. Okay. Just concentrate for 5 minutes. What is happening here? You will get in terms of matrix multiplication. This is what? Probability of push up after running. Okay. So what is this? Probability of push up after running is once again 0.4. And this is push up after push up. Okay. So push up after push up is this 0.1. Then this is probability of rowing after running. What is this? Running probability of rowing after running is 0.3. Then probability of push up after rowing. This probability of push up after rowing is 0.3. So here, see, these kind of multiplications are taking place. 0.1 is getting multiplied by 0.4. Look at this matrix clearly. 0.1 is getting multiplied by 0.4. Second multiplication, 0.4 is getting multiplied by 0.1. Okay. 0.4 is getting multiplied by 0.1. Third one, 0.3 is getting multiplied by 0.3. Third multiplication, 0.3 is getting multiplied by 0.3. Fourth multiplication, 0.2 is getting multiplied by 0.42. 0.2 is getting multiplied by 0.42. Can anybody tell me what is happening over here? First multiplication was 0.1 is getting multiplied by 0.4. Second multiplication, 0.4 is getting multiplied by 0.1. Third multiplication, 0.3 is getting multiplied by 0.3. And fourth multiplication, 0.2 is getting multiplied by 0.42. What is happening here? See here, if you take the matrix multiplication, okay, if you just compute p square, see here p square, how the matrix multiplication takes place. First row is getting multiplied by first column, then you compute the very first entry of first row of the result. First row is getting multiplied by second column, then you compute the second entry of first row of result, like this. Okay, here the sequence of this multiplication 0.1, 0.4, 0.4, 0.1, 0.3, 0.3 and 0.2 multiplied by 0.42. This sequence is nothing but first row is getting multiplied by second column. Okay, first row is getting multiplied by second column, isn't it? 0.1 multiplied by 0.4, then 0.4 multiplied by 0.1, 0.3 by 0.3, 0.3 by 0.3, and last one 0.2 by 0.42. What is the meaning of this? See, first row indicate this running, second column indicate this push-up. First row indicate running, second column indicate push-up. What is starting with running? I am starting with running and I am ending with push-up. Fine. In how many time steps? In 2 time steps. Because push-up as a second set, this is asked here. See, how likely am I to do push-up on the second set? That's why I am considering it as calculation of p square. It is p square. Fine. If it is asked, or if I just change this question, how likely am I to do push-up on the third set? Then what I need to compute? If it is asked that in the third set, then here previously I was computing p square. Now I need to compute p raised to power 3. P raised to power 3. Okay, and which entry I will be interested? Same entry. This second entry of the first row, because I need to start with running, I need to end with push-up, and 3 set workout is there. In that case, I need to compute p cube. Okay, suppose if I just change the question, if I start workout with a push-up, how likely am I to do pull-up on the second set? So what is the sequence? Start with push-up and end with pull-up. Start with push-ups, end with pull-up. Okay, on 2 sets. Then which entry I am interested in? 0.19. Are you getting this? This is nothing but structuring a problem with the help of Markov process. Now formally we will going to define this. What is Markov process? See here, it is the tuple in which we are representing these 5 things. First one, set of states. S is nothing but a set of states. If we take an example of this autonomous helicopter flight, so in which what will be the various states? The set of all positions and orientation, whether you are in the left side, whether you are on the right side, whether you are up, like that. A is nothing but set of action. This is the second entry in this tuple A. Okay, it is just a set of action. Whether you are taking a left turn, whether you are taking a right turn, up and down. Okay, so these are all the actions. Based on that perform action, you will move to the next state. PSA is the set of transitional probability. Like, what is the meaning of this? When you are at set S, what is the probability that you will perform action A? This is nothing but a transitional probability. What is the dimension of this? It is nothing but S cross A. It is a matrix. It is a matrix. PSA are the state transitional probability. For each state S and for each action A, there will be one entry which indicate the probability when you are at state S and you will take the action A. Suppose if we take one example in which 10 states are there and 20 actions are there, it means that you will be performing or you will be computing an entry or a matrix of size 10 cross 20, in which the first row indicate that you are at first state. What is the probability that you will perform action A1? What is the probability that you perform action A2 up to? What is the probability that you perform action A20? Moreover, summation of all these probabilities should be 1. Another thing, fourth parameter, that is gamma. We have not seen this gamma previously. It is considered as a discount factor. It is used for the calculation of the final reward. This is also known as discounted reward. Here see, it is closed in the form of in 0 side, but it is open in 1 side. It means that it cannot be 1, it should be less than 1, but it may be 0. It is known as discount factor. Another very important entry is there. This is known as reward. Okay, reward means you are at state S, you take action A. What is the reward that is generated? Whether the reward is positive reward, whether the reward is negative reward. If the reward is positive, then what is the amount of reward that you are getting? Okay, so this is once again reward. the dimension of this matrix is once again same. S cross A is nothing but the reward function. So with the help of these 5 parameters, we need to decide upon the Markov decision process. Now suppose total payoff and what will be the goal of reinforcement learning. See here, it's a sequence of decision, or we can say sequence of action. Previously you are at state S0 at initial level, you perform action A0, you come to this state S1 A1. Okay, then you take another action A1, you come to state S2. Once again you take this A3 A2, you reach to S3 and so on. Now see here, what is the reward generated of taking A0 action when you are at S0? Fine. Then what is the reward that is generated after taking action A1 when you are at state S1? What is the reward that is generated after taking action A2 when you are at state S2? Fine. See here, what is happening with the discount factor gamma? Here the power of gamma is 0. Here the power of gamma is 1. Here the power of gamma is 2. Based on this, what you can conclude? This is known as the final reward that is getting generated. And if we take the expected value of this, it is nothing but the total payoff. What we want to maximize this entire expression. Maximize the expected value of total payoff. This is our aim. Now, by looking at this particular expression, the aim is that 2 types of rewards are there. Rewards that is generated at later stage and reward that is generated at the initial stage. Okay. See here, 2 possibilities. Just look at this now. Here, reward is generated over here and the next reward is 0. Here, reward is not generated on the first action, but reward is generated at the second stage. Which one is better? Better is that reward received earlier is better. Why? Because just look at this formula. Here, suppose consider that gamma is equal to 0.8. Okay, gamma is equal to 0.8. So the expected value is this. Previously, this is the expected value. 2 plus 0.8, because 0.8 is a discount factor. But here, what will be happening? 0 plus 2 multiplied by 0.8. If you come to know that, this is the expected reward, which is better than the second scenario. So it means that reward received earlier is better than the same reward received later. Here, if you come to notice that reward is same. Here also reward is 2, here also reward, both the positive rewards are there. One more possibility. Here, reward received earlier is lower. R is equal to 20 positive reward. Here, this is later. Okay. At some point of time, you will get the maximum reward. Now, what it is saying, this 150 is getting multiplied by what? Gamma to the power some 100. Okay. But if you look at this gamma square or gamma, if you just compare this gamma square and gamma to the power 100. So suppose assume that gamma is equal to 0.8. So 0.8 square is nothing but 0.64. Okay, but 0.8 to the power 100 is very close to 0. It means that at a very later state, if you take very large amount of reward, that is compensated with the help of the power of this gamma. So what is the conclusion? Conclusion is this: larger reward, although received later, that result in a higher total reward is better. Okay, this is the case when you apply the formula of expectation over here. Fine. Now, some important terminologies, if anything is missing over here, the agent is there, which is taking action. Then it is interacting with the environment. This environment is generating 2 things. One is the next state and one is the reward, which is further received by the same agent. Like this is the next updated state and this is the reward. After that, it takes one more action, the next action more specifically. Now, defining your Markov decision process is based on these things. Suppose if we take an example of this tic-tac-toe puzzle in which we need to place this so that from straight line, it may be a diagonal, it may be anti-diagonal, or it may be vertical line or horizontal line. Okay, this is one example. Now, see, this is the initial state in which suppose your opponent is just placed one circle over here. This initial state is given as input to this. Now, agent decide which action that is going to take. Which agent means agent need to place cross over here. Okay, so agent decide. Okay, this is the place that on which I can place the. After that, this is interacted with this environment. Once again, environment is generating two things. See here, state, next state, and the reward. Okay, see here, when you are at this particular state, you place over here, no reward is generated, so neutral reward is generated. Reward is equal to 0, because at this point of time we don't know whether we have won the match or whether we have lost it. So here neutral reward is generated. Just look at this, plus 0 means neutral reward, and this is the next action that is generated. See here, it is a game in which you take some action, then environment, then another action. Based on that, you take next action, then once who is accomplish this placement in a straight line. See here, it is a sequence of time steps. This is time 0, one state is there. Then time step 1, what is happening? Time step 2, what is happening? Okay. MDP means Markov decision process. Iterates over a sequence of time steps. Okay. Steps. At some point of time, the opponent is successfully placed all three things in a row, or in a column, in a diagonal, or in an anti-diagonal. Then that is considered as a terminal states. That is considered as a terminal state. The entire all these steps considered as a one episode, means one game. Okay, you may also play several number of games, like suppose you play this game 10 times, so 10 episodes are considered. In one episode, these many time steps are there. It is also possible that in episode 1 10 time steps are there, in episode 2 only 6 time steps are there. Are you getting the concept of episode and time steps? See this, episode 1, this is like that: state, action, terminal state. Terminal state means either you or opponent win the game. It is also possible that at some point the game is just halted, nobody can win. Okay, this is episode 2. Just look at this. It is possible that nobody is the game. It's a draw. Here, see, states and based on that we can then, okay, what are the vision this action, and this action to this state. If you take this action, you reach to the end of states. Based on this, you can draw this state transition diagram. On top of this state transition diagram, you can come to notice that what is the reward that is associated with taking action 1, what is the reward that I will get after taking action 2, and so on. Based on that, it is getting generated, and after that we will get some terminal kind of states, and some of these states will be just halted states, means you cannot move further. So 3 important things are there from which I can conclude the today's lecture. One is return, the total reward over all the time steps. Policy means what will be the policy of playing the game, on which policy I am taking the decision. This policy is decided by the agent. Okay, it may be a deterministic policy, it may not be a deterministic policy. What do we mean by deterministic policy? One deterministic policy is that I will always select one action which is giving me highest reward. This is one policy. What is the deterministic policy? One more deterministic policy example is that in the previous episode, if I had run this particular action and I lost the match, so definitely I should not choose this. Okay, so this is one more policy. One more, what is the example of stochastic policy? Just randomly place any particular, randomly place any queen at any particular position. This is known as stochastic policy. What will be the value function? It represents how good is each state and or this action, which indicate that one value function will be associated with each and every policy. Based on that, it is evaluated. Okay, and this is the expected return. Finally, yeah, before this policy, we just look at this. We just look this. Okay, see here, using this, we can define the policy. This is the expected return when this is initial state S, and this is your policy pi. Our I want to maximize this value. We want to maximize this value when it is surrounded by the policy pi. This is our objective function. Okay, and it is known as the Bellman equation. It is known as equation is a backbone of this option, or we can say of all the objective function that is adopted in reinforcement learning. Every time you are defining some sort of objective function based on some policy and the decision equality, these are the various examples of the policy. Always pick the next section at random. It is a stochastic one. Always pick the next state that gives the highest known reward. Known reward means in the previous episode you are having some sort of previous state. Then I had got the maximum reward. This is and what you do, just pick that next state which is giving you the highest known reward. Another one is this: take chances and explore new state. What do we mean by this? There is some possibility like option 1, option 2, option 3 are there. I clearly know option 1 is better, but I will take the chance. I take another state. It is nothing but this policy: take chances and explore new states. In what hoping that I will get hope in future. One more policy is there: always play in a safe game. Always play in a safe mode. Okay, do not cross the limit. Suppose if you are moving from safe to unsafe state, then we will not move particular action, or we will not take that particular action. We are not going into the unsafe state. So these are all the policies. Yeah, deterministic versus stochastic policy means if some sort of randomness is there in choosing the policy, this kind of policy comes under the category of stochastic policy. Otherwise, this is known as deterministic policy. Relationship between the reward, return, and value. Reward is what? It is the immediate reward. Take the action, you get the reward. Maybe positive, negative, neutral. Okay, and the magnitude of reward is very important. Like how much reward that you are getting. This is considered as a reward. It is associated with a single action. Return. Return is the total payoff. Total of all the discounted reward. We had already seen the formula is reward generated at first time step, reward generated at second time step multiplied by discount factor, then plus reward generated multiplied by discount multiplied by factor, modes like that. This is the return. Value is nothing but the minimum return, or not minimum, but the minimum, not the of all the expected value of all the value, which is average of all the returns over multiple episodes. Like see here, this reward associated with this episode, then sorry, not reward, return with this particular episode, then with this particular average, it is no. known as value function. Value function is described with the help of Bellman equation. Okay, fine. If any question is there, if any question is there, then you can ask. Yeah, if you are having any question from CNN also, then also you can ask over here. In the implementation of convolutional neural networks, if you are having any doubt or any doubt or any doubt difficulty. So everything is clear and fine. We can close this meeting. If you are having any query, then you can ask. Thank you. You can ask. The implementation of reinforcement learning will take another half an hour. It will take another half. Make sure that you understand this Markov decision process. If you can formulate or if you can solve the problem as a Markov decision process, then it's fine.
No further questions? Okay. Thank you, Dr. Dr. Tausif, for the wonderful presentation. It was really lovely to
Thank
have
you,
you
ma'am.
for 3 sessions in this workshop. Thank you so much, Dr. Tausif.
Thank you, ma'am. Thank you, ma'am.
Tausif?
Hello? Yes, ma'am. Thank you.
Okay, so we'll have the next session at 3:15 by Dr. Emmanuel Pilli from MNIT Jaipur. Please don't miss that session. Just after 15 minutes, he would be there. And we'll see the biomedical applications by him. Just let me check and confirm his topic. Yeah, he would be talking about intrusion detection using ML algorithms. So that would be another applications of ML algorithms, intrusion detection. Please don't miss that session after 15 minutes. I'm not closing the meeting, so please, all the participants can stay in the meeting itself. Thank you so much.